All right, thanks for joining me tonight. Man, this we had our 10-year anniversary at Springfield Devs this year or last year, one of the two. Now we're at our 11th year. Had a crazy year, and I thought it'd be kind of fun to shake things up a little bit. Normally, uh, we don't have what I consider to be extremely technical talks, but I thought it'd be kind of fun to go that direction tonight. So everyone who's joining me tonight, y'all are the real nerds, all right? And be proud of that. It's okay. It's okay. Um, you might have a lot of questions tonight. I encourage you to write them down so you don't forget. And yeah, let's have some fun. So I need to turn this on. This is why I don't do live demos. All right. Awesome. All right. Hi. My name is Fred. I'm a systems engineer at Cloudflare. I love PHP. I love telling people about PHP. PHP is awesome. I used to write PHP code. I don't anymore. Also used to write JavaScript code. I don't do that anymore. Instead, I write code that your code runs on. I'm being serious. Y'all are running on my code right now, whether you know it or not. So we're going to kick things off with what this whole presentation is really about. The Holy Trinity. God the Father, the Son, the Holy Spirit. But this ain't a cult. We're all nerds. I mean this Holy Trinity. The thing that started everything. C the language, C the standard library, C the runtime. But not many people understand how pervasive the Holy Trinity really is in our daily lives. It's Rusty. So I write a little program here, a little hello world, basic stuff. Compile it, run it. Hey, look at that. It's C. Now, it's not quite obvious, but we can look right here in the output of this command LDD, which tells you what dynamic libraries are loaded into this application. We can see that we have libc.so, that's your standard libc library. We have LD Linux, that's the libc runtime. We also have this little thing, libgcc whatever for GNU or something like that, right? What about Go, right? Is Go C? Oof, no. When we compile and we run it, it is not. What's going on here? It's not a dynamic executable. What does that mean? I don't know. We'll find out. Let me do this. Why don't C is supposed to, or Go is supposed to be interoperable with C. So we add a little import statement in there. Hey, there it is. That's what we're looking for. So what's going on here? Well, the reality is that Rust is designed to be interoperable with your systems. Go is also designed to be interoperable with your systems. But the thing is that Go is more user-land friendly than it is system friendly. But you can use it for both. I personally like Go. It's great. But here's how it works conceptually, right? So what I just showed here is the difference between a static library or binary and a dynamic binary. Static binaries are compiled with all of the dependencies basically baked into them. Dynamic libraries or binaries are the opposite. All our dependencies come from somewhere else on the system. And the key here, though, is that when you statically compile a program, you have to ship it with a runtime. Now, this runtime can come from anywhere, but really, if you're writing it, if you're doing something like embedded development, right, you're kind of writing your own little runtime, right, whether you know it or not. So, but here's the thing, though. These binaries, whether they're statically compiled or dynamically, may eventually actually use the libc runtime. So Golang, for instance, is a really interesting case because even if you manage to import a library that uses C, for instance, and you statically compile it all, it's still using C underneath it. Even though when by default Go has its own runtime and doesn't use C by default. Same thing with Rust. You can make Rust be static, but you're shipping and compiling the runtime with it at the same time. This is how .NET C# works also as well, right? But the real difference here between Rust and Golang is that Rust is purely compiler, Golang is purely language. So I'm going to make the argument tonight. C, Go, Rust are actually C. Terms and conditions apply, of course, right? Like it's not always the case. I've been saying a word tonight called runtime, right? So what this presentation is actually about is we're going to be building a C standard library a C runtime with the C language. Now, I'm obviously not going to go into all the details, right? Like, that'd be boring to just look at code all day, right? But we will see some assembly. So let's go ahead and dive in. I've been working on this tool for a while now called bmath. It's a little calculator. I use it for debugging and doing binary operations all the time. And it's really helpful to look and to see what numbers are behind the scenes. Now you might be thinking, well, why not just use like a normal calculator or whatever? But the thing is, though, is that this actually has a lot of features I like. Right? I can pipe in a file from standard input. I'll read it out. I can write output to standard out. I even have a little watch mode, so I can open up Vim and pretend I'm programming in this little calculator, right? So it's a really nice little tool that I use for debugging all the time. But here's the neat part. I also have it as a loadable library. So you guys tonight could actually go ahead and download this code, write a little C program, or not, more on that later, and you can actually use and run this on your systems as well. And I have a little example code there where we import the library into this little example.c file, and we have some code there that sets up the parser and executes the code, and then it outputs pretty things with the print all function. But what about PHP, Python, JavaScript, or any other language, right? How am I going to let people use this tool in these languages? Now, you might be thinking, okay, well, we can just go ahead and shell out, right? But you're creating little processes all over the place, all this other stuff. Really, what you want to do is you kind of, the ideal way to use this tool is to actually embed it in your actual applications itself. So the question is, do these languages actually contain bindings to do so? Do these languages natively have interfaces to do this? Well, the short answer is typically you don't, right? We're all high-level developers. We ain't got time for that, right? But here's the thing, though. Python developers love this stuff. All right. Here's some little sample code I have going on here to actually write the test cases for tonight, as a matter of fact. But generally speaking, for PHP, I don't know if you can load in libraries into it, JavaScript, Node.js. I'm sure you can. I don't know how to do it. But the reality is that typically we just don't do that, okay? Like, I mean, we like simple things. We like nice little interfaces. So in order to embed this into other languages, I have to think of like, okay, well, what's a good interface that all these languages have in common? And the funny thing is, files, right? All these languages can open up files. They can read files, write files, close files, delete files, do whatever the hell they want with files, right? And that's the sort of interface we're kind of looking for. Something like this. We open up Python, open up a path to the file, write in our little expression, and then just read it out. Simple. Even better. Well, now we have ways we can control how we actually display this output with IOCTL, which for those that are not familiar, IOCTL is a way to set different settings and whatnot on various files on a system. I don't know if it's on Windows, but certainly Linux for sure. But here's the kicker, though. You actually need a file in order to do this. And that's where kernel modules come in. So the neat thing is that we can use Linux to create what's called a device file, in this case, /dev/bmath, that's going to act as a file that we're going to open up, read and write to and close, and do whatever we want to do with that. And device files are really interesting because they come in a few different flavors. Sometimes they can come in as block devices. These would be like your hard drives, things like that. But more often in case, you're going to come across what are called character devices, which are very purposely built for this purpose of reading and writing to constantly throughout your systems. So, what is a kernel module? Kernel modules are little programs that you can compile and inject into Linux at runtime, compile time, what have you. And it's a really, and what separates them from device drivers is how they're basically loaded into the system at boot time. But the general gist of it is that kernel modules are the way that we can create files on our system for my little interface to interop with. So you might be thinking, okay, well, the logical thing then is, okay, well, we're going to create a Linux kernel module to do this. That seems simple enough, right? I just go into my repository, copy and paste some code around, compile it, all that's good, all that's swell. But here's the thing, though, that's just too much work. we're really maintaining too many different repositories at this point, but that's not what we're about tonight. Oh, hell no. We are going in. We are going to load this sucker in to the Linux kernel itself. I'm a PHP developer. I love PHP. I also like clean code, and I hate repeating myself. So that's exactly what we're going to do. But first, we need to understand what is a binary. Windows has them. This is called a pcof file, or PE, portable executable, for those that aren't familiar. Ever wonder why Windows always talks about having, oh, we have the best backwards compatibility and whatnot, blah, 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 blah. It's this right here. They support DOS. They support COF. Portable executables came from COF. COF was like one of the original binary formats that existed. And here's a pretty picture of how this might look. Mac and Apple has their own. They call it Mach-O. I call it Macho. I originally thought it stood for machine object file, but I guess Apple's kind of lame and decided to go with Mach-O instead. I don't know. But it's similar to Windows, right? We have similar layout. We have some header at the top, some information describing the file, yada, yada, yada. Well, Linux is no different. Sorry I couldn't have a better photo of this or a better picture, but as you will find out, Linux folks love words, not pictures. So, same thing. We have a little bit of a header, and we have what describes the rest of the file. So let's actually take a little deep dive into that, right? So this is what the elf header, or this is what the elf header actually contains. I've highlighted the actual more important detailed points that we're actually going to focus on throughout the rest of this presentation. But to start things off, highlighting the type. So this is important because it kind of tells us what exactly file we're actually looking at here. Now, binary files come in many different flavors. One of them, in this case, is actually a dynamic one, which means that it's meant to be loaded dynamically at runtime. Notice how the entry point is zeroed out, right? On an actual typical binary, like say you run that LDD command from before, that will actually have something present in there, an address in there, that when this program actually starts and runs, it's going to jump to that and start executing. Not in this case. Then we have what are called the program headers. More on that later. Very important, though. The size of the program headers, the number of the program headers, and then lastly, the actual index in which the strings for all the sections appear. So they have their own built-in lookup table to actually look up strings to fetch from indexes to print them out more easily, and so you can actually look at them as well. But to kick things off with program headers, this is what they look like. There is a lot of things here, all right? I don't know about you, I go cross-eyed, so it's better to actually highlight these things instead. So really what program headers are is they describe the contents of the file. So each of those program headers correspond to sections within the actual executable itself or binary itself. And the ones that are kind of really important that we're going to be focusing on tonight are segments sorry, I said sections. I meant segments. So these are segments. So the program headers section describes segments, which segments are logical groupings of sections inside the ELF binary format. And we're going to be focusing on these highlighted ones, where the one highlighted in bold is where your code actually lives. This is where all of your functions, all of your code, all of whatever you have actually lives and executes from. And then in the let's see, in the 03 one, that's where all of your global variables exist. All of your string literals, all of your, well, unless the compiler gets rid of them, integer literals, all of your literals exist there. And I'm not going to go into too much detail of the rest of it, but essentially, segments are the most important part when it comes to loading these binaries. And for all you hackers out there, this is what you need to focus on, right? If you're going to be patching binaries on the fly, maybe not even on the fly, maybe before you ship the code or whatever, right? Like if you're going to be patching binaries, you want to make sure that whatever code you put in here goes into that text section, and you want to make sure that you're not adjusting the file sizes or moving things around. Use a technique called code wells to actually implement your code in and patch it into these executables without having to affect them in such a way that they didn't break when you go and execute them. But moving back to the actual headers, these are the different types that we're going to be looking at tonight. More importantly, or specifically, the load type. So the load type is essentially the kind of header that tells you how to actually load all that code into memory. We'll talk a little bit more of that in detail. Dynamic is interesting because the dynamic contains all of the information that I need to actually dynamically load this library later in the code. And we have a few others in there. We have note, we have some GNU things, right? They're not really all that important for this presentation, but they're there. Sometimes there's more, sometimes there's less. And the way the loading works is you start off with alignment. So you have a file size, you have an offset size, all these other things involved with loading. But the thing to remember is the alignment, okay? Fun fact, OX 1000 is 4096 in bytes, which means that all of these load types are aligned to page boundaries in Linux. Okay, so page boundaries are logical blocks of memory that are, and that's essentially how the Linux operates memory in a way. Like you're not going to get like different weird sized blocks. You're going to get things done in pages, and this is important for when things go into swap, come out of swap, go into memory, out of memory, whatever. Right? Move around, swap around, virtual memory, lots of memory things. But we're not talking about that tonight. So the thing, though, is that the alignment doesn't necessarily matter as much for the other segments in this file because we're not really going to be touching those. What really matters right now is that when we load these into memory, we have to calculate their sizes to actually allocate enough memory to then load and align these blocks of file memory into the actual kernel. I'll actually show that in a bit. Next, we have our actual permissions. So I talked a little bit about loading them, but now we need to actually protect that memory. So when it comes to loading binaries and libraries, you got to make sure that you set the correct access permissions because guess what? An attacker is going to come in there and be like, oh, wait a minute. This block of memory is executable? It's read and write? Arbitrary code execution. Let's go, right? Like that's how that works. So R means read only. RW means read write, of course. RE, read and execute. And there's a couple of other combinations in there. Sometimes you might even come across one that's like NX, I think, which means no execution whatsoever, like never. But this is important because the actual hardware on your machines is going to use this information to actually grant or deny the processes on the CPU to actually, whether or not they can actually access and run things on this code. So, oh man, more on this later, let me tell you. So, as a recap, the dynamic segment provides details on how to load symbols or functions, but this is what the file actually, this is what that section actually looks like inside of the code here. Now, I'm not going to go over every single little detail here, right? Because like this is a lot, right? Like what's a PLT GOT, right? Jump rel? Who ever heard of that? I sure haven't. Maybe we might. No, I'm just kidding. We're not going into that. Trust me. That's a whole can of worms. So, you know, there's actually a lot more here that I'm not showing, but, you know, screen space and what have you. But the idea is that we're going to be using this information to actually determine how we're going to relocate symbols. Now, symbols are the same thing as maybe global variables or maybe function names. So if I use the word symbols throughout this, I'm going to be talking about functions mostly. So, what does that mean? The dynamic symbols, everything highlighted is missing in this file. So anything that has the undefined index means that this comes from somewhere else. So recall earlier I used the command LDD to actually show what dynamic libraries are going to be used for that binary. This is it right here. These are all the functions that are in theory going to be used by my library. Ooh, and we have to account for that. So let's all put it into practice. All right, starting off, we're all good. We set up all the plumbing. We load in the library. We got our little binary blob from the file from the disk. Now we got to actually calculate what size it is. So what we do here is we actually loop through all of the load statements in the headers. We calculate the size that we're going to need. aligned to the next page boundary, and then just add that all together. And then eventually we go ahead and we allocate this memory into a big old blob. But now that we have everything, now that we have our blob, now we got to start copying memory over. Now, traditionally, when you're loading binaries, you're not actually doing this. You're not actually copying everything into memory, but you got to remember, this is kernel land here, okay? We're actually in the kernel module at this point. So we use this memcopy function to actually calculate the offsets of the file that we're trying to copy the information from and put it into our big old blob. But after we're done copying it, we need to protect it. So this is what we're, oh wait. Oh shoot, I jumped ahead. So then at the very end of that, then we protect it with the protect section function. More on this later. But from here, this is where we're actually going to be protecting the different sizes and page line boundaries of our memory. Symbol relocation. So next, after we've loaded all of after we copied everything into our blob, now we're actually going to do the symbol relocation. So I have this little function here called handle dynamic section, which basically just goes through that dynamic section that we looked at earlier, caches all those offsets so I can, I like global variables. They're all right. Caches all those offsets so then I can then use those to then determine how I'm going to relocate symbols within the memory itself for the executable. And then that's where we do the relocate dynamic symbols and relocate PLT. I'm not going to go into PLT tonight. I thought about it, but no. We're not doing that. But we're going to be talking about this relocation anyway, right? But so when we actually get into the relocation, what we're really doing is we're saying, okay, there's different ways to perform this, and this is all done through this little switch statement here. I'm not going to go into too many details about what each of these little things are, but there is a prescribed way to actually relocate functions within a blob of memory for binaries, and this is how it's done. We take the pointer address, and then we go ahead and assign that the value for the address. So if those of you that are not familiar with pointers, essentially that first line there on the relative, I have a pointer to address, so I'm dereferencing the address, and I'm setting its value to the new point where we're going to actually call this particular function that's within this relocation here. So we're going to put it at the offset of the blob plus it's what's called its addend. Now, not all of them use an addend, right? Some of them have other relocation strategies for example, the x86-64 and the jump slots and the glob jump slots all do a similar relocation. It depends whether or not the symbol you're relocating to already has a spot in the binary itself to relocate to. Otherwise, it's not going to do anything. And that's where the dynamic symbols come into play. So this is kind of how it works. All those functions kind of just call in this little internal relocation function here. At the very end is when we do our last final relocation. And this handles it for all of our dynamic symbols. This handles it for all of our other symbols that actually have relocation points within the binary itself. And then that's it. We're just going to run it, right? Right? Yeah, wrong. No, absolutely not. No. Nothing ever works the first time. This wasn't even the 100th time that anything even worked. You know what I'm saying? Like, nothing ever freaking works. And now it's the fun part of the presentation. I'm going to complain at you for the next however long it's going to take, starting with defeating security features of Linux kernel itself. Recall earlier protecting memory? Yeah, that one right there, protect section. Well, typically what happens is when libc or user space gets involved to load libraries and other and things like that, they're using what's actually called the memmap system call, which essentially just kind of puts a little window over the file, and you put it at page line boundaries, and then you tell it to go ahead and allocate this amount of memory for it and protect that memory so that others who are having access to this process can't actually do anything nefarious with it, right? But this all happens in user land, right? So when we're talking about runtimes in libc, they're actually calling these memmap functions. So if we run a little strace, which is a syscall trace command in Linux, and trace the open@, and the memmap, you can actually see when you run the bmath program, this is one of the first things it loads, and it puts everything into memory, and it protects those pages. But this is what Linux has. So in actual Linux code, at this header file, these are the functions you have access to. But here's the thing, though. You don't actually have access to these functions. They're what's known as unexported functions. So back in Linux 4.0 or something like that, they made it so you couldn't actually call those functions from your modules anymore. So that's where ASLR comes into play. So ASLR, from a user space perspective, is a security mechanism to randomly relocate those memory mappings within the process's memory space. This makes it very hard for attackers to find and guess where your functions are actually located in your code to exploit it and to do things with. So it's usually not a very good idea to ever disable this. But we sure are. We're not going to do it on the Linux level, but I mean, you can if you really want to, but we're actually going to hack this, right? So here's the cool thing. These functions aren't actually exported, right? But here's the thing, though. When you download a debug build, maybe not even a debug build of Linux these days, in the boot directory, you might see what's called a system.map file for the kernel version you're actually running, and it has the list of all the addresses from the actual Linux kernel itself for all the functions that are within it. Pretty neat, yeah? There's also another way you can do it at runtime, too, if you have the proc kal sys enabled. But if you're not sudo, when you run this, you get 0 addresses. It doesn't tell you where they're actually located at. So what we actually end up doing, then, in this case, is we take all of those addresses and kind of put it into this little template. So at compile time for my little module, I have a little Python script that goes through that system map file, finds all the addresses I need to find, and then kind of just inserts the raw hex into this header file, and it ships as a header file with the actual program. Then it compiles with it. Then, because I like clean code, I said it before, right? I make little wrapper functions to kind of pretty this up. Now, what's this? KASLR? What the hell's that? Ah, the actual defeat. So when it comes to defeating KSLR, all you need to do is find a function that is exported to modules and then calculate its offset from where it is actually in running memory. And with that offset, we have now defeated KSLR. Normally, you need to hack the kernel to do this, to find these addresses, but this is part of the reason why maybe kernels don't even ship these system map files anymore, because you can actually leverage them to defeat KSLR. Thus, we actually have our memory protection. Pretty neat, right? Oh, we're just starting, though. Stack Protector. Who here knows what Stack Protector is? Cool, we're about to find out. No one raised their hands for those that are watching on Twitch. So Stack Protector, so where ASLR prevents attackers from finding functions to exploit within your code, Stack Protector makes it so you can't do ASLR attacks by protecting your stack from stack overflow buffers or overrides. Right, you just load it into your program in this little register. It's purposely random because you don't want attackers to guess this, because if they can guess this, then they can actually exploit the fact that, oh, well, now they know that after they perform their buffer overflow to go ahead and reset that variable back to what it was. And I don't know if I may have forgotten to mention, but the way Stack Protector works is that it injects a variable at the very end of all of your other variables and then assigns it this value. And the idea is that if you perform a buffer overflow, if you have an array of, say, like 100 bytes or something, right before that, and you overwrite that past to 101, guess what? It's changing the value of this variable. So when it checks at the end of the function, that's how you know that your stack has been compromised. Oh, that's a lot. Whoops, I didn't mean to click that button. So anyway, that's what we're doing right here. We're going and we're getting this random value. Why it's lopping off the last byte, I have no idea. My guess is that something wants to read this and wants it to be a 0 byte. I don't know. But why does this suck? So the interesting thing is, though, when you're writing these kernel modules, the thing is that the Linux itself is constantly swapping its own memory, its own processes, its own internal threads, etc., all over the place, running on CPU 100, then next on CPU 2, CPU 30, right? It kind of just bounces around, and there's these things called IRQs. When these things like IRQs come in, they're high priority. That CPU is going to execute whatever code that comes in there almost immediately, right? But here's the thing, though. We're dealing with like some global state here, right? So basically, when I'm trying to, we need to create like these little, what I call guard wrappers, that are going to protect the functions for my library when I actually call them. So we have an example right here, guard call for. So basically, when I call the parse function from my actual library, I'm wrapping it in this guard. I'm passing it its own instance of its own thread local storage. So it's per invocation here. And then the actual arguments get passed in immediately after that. And what this does is it allows me to essentially protect this FS register. So when the processes swap in and out, not all registers actually get copied over. The FPU ones, the floating point ones, are notoriously meant for blowing away and doing whatever you want with them, right? So they may not get copied over. And the FS register is no different. Now, in my testing, I found out that the FS register kind of doesn't get touched very much, but we do need to set it back, though, after we change it, because once the kernel calls code after this, if it's not set back correctly, crash, 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 crash. That's the story of this whole presentation, is crash, 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 right? So now, I was being a little extra protective here, and I decided to protect it anyway. So we go ahead and we set the FS register to our memory allocated for the TLS, the thread local storage, and then we go ahead and we set the address to the FS register and everything's good. Oh no, it's never good. So remember earlier I said that we don't necessarily need to implement every single libc function? Well, that is very true, but you know what? I need water. It's a game of whack-a-mole. Which functions do you need to implement, right? So this is where Batman gets involved. Batman's an investigator, right? Vigilante, investigator, he does bat work, right? Good bat work. Oh no. This is what you're dealing with. When you come across whack-a-mole situations, you get these nasty little error messages saying null pointer dereference. But when you look at that, you're like, what? It's 2d6, what do you mean null? That ain't 0. Well, kernel don't care. If that address was more filled out, it might say a different kind of page fault error message there, but in this case, it's like, well, there's enough zeros, this is null. Clearly it's not. Not even Alfred knows. Ooh, plot thickens. Rob is trying to be helpful, because if you do an object dump on the actual library, we can find that when we grep for this actual address, oh wait, look, there it is. Can anyone tell me what snprintf check might do? No? What was that?
Prints the statement to standard output.
Ah, yes. Stack protector. There it is, right there. Not really. This is another security feature on top of that. So Robin is correct, right? This actual code and address actually exists in our actual library, because if we go back here, we don't actually have any traces. Now, I kind of clipped it off, but we don't actually have any real information of where this actually exists. So it's actually a pretty safe bet that it's coming from this file right here. We can kind of see that, oh, it's this function right here. Maybe I didn't implement that. Batman's right. That's not what I meant. We know it's there. But we have to actually implement it ourselves. So the thing about loading in binaries dynamically, either through user space or the kernel, what have you, right? Any library that you also don't also import in and relocate all the functions for, you have to implement yourself. And that's exactly what's going on here. So all of these functions I have to write out basically by hand. And let me tell you, there is a thing called the I have it in my one of my later slides, but essentially it's a long document of all the functions that are ABI compatible with Linux that you have to implement if you're going to execute these in your code. So that's the neat part. You do it yourself, right? You make these functions yourself. That print statement, oh yeah, Linux doesn't have print statement. Now you might be thinking, well, sure, you have VSP print right here, right? Okay, I got you. Yeah, it does have it, but it doesn't have libc. You still have to implement these functions yourself. That's the thing about running code on embedded devices, when you don't have these libraries around to call these functions, you have to invent them yourself. Linux did it. I'm doing it here right now, but it's a little easier for me because I have some help from the compiler and Linux to be able to do this. And it just makes it a little bit simpler. And you can see we have a little malloc call up there. We have to call kz alloc, which is Linux's way to allocate memory, and then I have atomic on there to make sure that it doesn't happen to sleepable state. We're not going to talk about that. Next, we have file. So typically when you work with libc or any sort of program, you have to open up files, delete files, whatever, right? Like you have this thing called file. It's a pointer, but here's the thing. When you're working with std error or std out, which are the standard file descriptors that pretty much all your processes get, you have special meaning. We have to implement that ourselves too. We have to relocate these. If when my binary uses these two variables, we have to actually create them and relocate them and use them ourselves. Also implement them too, right? I had to write my own little wrapper functions to make my own libc functions, which the kernel doesn't have to support this file pointer that comes with libc. Pretty basic, just memory backed, no big deal. And this is how we actually add these symbols to the relocation. So if you recall earlier, the functions had like a little rsins parameter being passed in. That's what this is. So this is a file that I have in the module that lists out hand-coded all the different variables that I need to relocate manually in my application to make it run. Right? We're gonna ignore icon v. Like that's a whole can of worms. But libc for the moment right now, we're taking all these functions and we're dynamically relocating them when we actually execute and run my binary. Batman approves. We could just load in more libraries, but we ain't gonna do that. No. What happened here? All right. When I say dramatic start, reenactment start, this is all contrived from here point forward. Real situation, it did happen. I just forgot what commit it was. So we're gonna manufacture it. Okay, all right, whatever. Make a change to my little library. Make a pretty big array to be not as big of an array. Shortened up a little bit. Nice little commit. Works out well. Ooh, no, it did not work out well. What on earth is this? Right? We have to we have this the stack trace here underneath the task symbols, but what is all this? Where is this even happening at? I've never seen some of these addresses in my entire life. I have no idea, but you know what that does have an idea? Linux has an idea. That's right, folks, we're going to disassemble all this and actually see what it does. It does this.
Oh, great. Just a bunch of turds.
Oh, there's a saying in the South, it's deeper than whale shit. That's kind of like what this is too. This is deeper than whale shit, let's be honest here.
Yeah, there's a bunch of turds.
Sure, right. Okay, so diving on in, right? So we have our little assembly code here. So we kind of have to decode what's actually going on. But the nice thing about the decoder that ships with Linux source code, not so much on Debian anymore. I don't know why Debian doesn't do this, but you can get this thing called decode stack trace. Pass in your Linux binary. Pass in the debug one. Keep in mind the debug one. Pass in the stack trace from before, and it gives you this pretty little dump right here that tells you, yeah, pretty dump, ironic, I know. It gives you a pretty little dump here that tells you exactly where the code failed at. But here's the interesting thing. The trapping instruction on a move APS to from or I guess this is AT&T syntax. So from this MM0 register to whatever offset that is in the program stack, right? Okay, I'm reading this. Okay, all right. There's some funky things going on here, but just how funky is this? Okay, so we have the decoded. So I kind of switched the syntax here to Intel at the bottom. So you get it's the reverse of AT&T. But when you actually decode this in Ghidra, right? You open up Ghidra, you take a little library, you go to the part where it failed at whatever, right? And then you go ahead and decode it. We get this. What the hell is this, right? Oh, by the way, there's stack protector. Yeah, right there at the end. But what is this? What is happening? Okay, so then, through some trickery, we can just look at the code and then find out, all it's doing is fast zeroing out memory. That's pretty neat. 8 instructions to do 128 bytes in one go. Not bad. Not bad. But that doesn't tell me anything, right? It just says that all we're doing is zeroing out memory. Like, how does this go from this to this? Like, what is the actual problem here? And in fact, there is a clue. The stack variable itself. So every function has what's called a stack frame that goes along with it, and RBP is the register that contains that stack frame. And by some miracle, I learned how to Google during this problem, and I learned that the move apps requires single instruction, multiple data instructions or registers as well, right? So these are a fancy way to do more work than you otherwise would in one instruction as opposed to lots of instructions, right? So 128 down to 8, right? But here's the thing though, when you read a little bit deeper, in between the lines, it has a little note that says, oh, by the way, all of your memory needs to be aligned to 16 bytes. What? I don't know, it just needs to be 16 bytes, and that's exactly what was happening here, right? Everything was aligned to 16 bytes. But when we use bmath, I know ironic, when we use bmath to figure out what the alignment is, we find out that it's actually aligned to 8 bytes. Linux kernel actually aligns all of its code basically to 8 bytes. Why it does this? I'm a little fuzzy on the details. There's a lot of technicalities here, but essentially the kernel is doing optimizations that even the compiler can't dream of, apparently. So that's fun, right? So we need to fix that. Remember that little guard function we have? Perfect opportunity. So the little trick here is, what I'm doing is I'm telling the compiler with this volatile keyword, do not mess with this variable at all, right? And then I'm using another compiler feature called align 16 to say, with this variable, align it to the 16th byte on the function stack, okay? And then you have to use this unused thing because, compilers complain about unused variables, whatever, right? So the idea here is that if the stack is already aligned to 8 bytes, force it to be 16. If it's already 16, great, add 16 more, right? So that's essentially what we're doing, is we're tricking the function stack frame to realign its memory such that when we actually call our code, it will actually perform the single instruction multiple data thing, in this case the move, to do the fast zeroing out all the memory, and everything works great, right? Not so great. There's still one more piece of the puzzle. Everyone heard of threads? I sure haven't, right? But they kind of do this. When you have a single binary or memory blocking code and you have multiple things accessing all at the same time, well, what happens to your output if you don't allocate specific memory to each of those things? Well, it gets jumbled together. So this is one of my test cases. It just failed, right? Like what is all those zeros in front of this, right? And it starts off on a new line. What the hell? None of it makes sense. And the thing about files is that you're in theory supposed to be you're allowed to open, read them, do whatever, right? All in parallel. And that's essentially what is happening right here. So, recall how I relocated string or out and error, right? All those things were global, okay? So they get all messed up when you're writing to these files. So, but here's the thing though, writing is actually okay. Now, I didn't mention this at all up until this point, but the way this module works with files is you write to them, yes, but execution happens on read. Did you know that it's really hard to detect when someone's done writing to a file? I sure didn't. I learned the hard way. So I made an executive call to say, well, let people write whatever the hell they want. And we just know that they're done when they read it. So the solution then becomes quite simple. Just write locks. Synchronizes everything together. Yeah, that's typically how you solve synchronization problems. I mean, there's really not much to it. So there you go. There's a diff of me locking every single read. All right, one more time. We're gonna run this one more time, right? What do we get? Not a live demo. So I'm gonna run make clean. Gonna clean everything up just to show everything works. Gonna go ahead and compile with make. Takes a minute. Gonna go run it. Spins up a virtual machine. Go ahead and run the test runner. Boom, there it is. All tests pass. This is where you clap. Recap. What we learned tonight. The Holy Trinity. C is pervasive. It's everywhere. If you want to get rid of it, forget about it. It's going to take another 100 years. All operating systems execute some type of binary format. Windows got PE, portable executable. Apple's got Macho. Linux has ELF, right? Binaries are structured for easy loading. I mean, we all saw the code. That was easy, right? Runtimes are a pain in the ass. They have security features that you have to contend with. Writing your own runtime sucks. Was this whole project necessary at all? No, the answer is no. But if you've ever seen Futurama, they have an episode they're like, a what if machine, right? This wasn't a what if. This was, wouldn't it be crazy if, right? Like, this is kind of crazy. So this project was a whole lot of work. It took way more time than I care to admit, but there's a link to where you can actually download and run it. Do not run this on your production machines. It does exploit KSLR, and it's not coded in such a way that it's going to protect you. But at least you can run it up in a virtual machine and it works great, right? So PHP, saved. Node, saved. Python, it does whatever. Saved. Ruby, saved. Whatever, right? It's all saved. We can all use files. Here's some additional resources in no particular order. Good luck reading all of them. Yeah, that's it. I'm taking questions now.
Oh. Go ahead. That's fine.
2 questions. Will this be on the test? And what DEF CON village are you running this year in August?
None.
Oh.
To both. Both or none.
Oh, you're going to DEF CON.
What? No, we're not going to DEF CON. I don't know where you got that idea from. That ain't happening.
I heard that you were going to DEF CON.
No, we're not going to DEF CON.
We had such fun at the last con.
Questions.
So, getting around KSLR is something that sounded necessary, but is there like a better way to go about making a kernel module than hacking that?
I mean, no. I mean, in general, the answer is pretty much no. So this is a very special case where I needed to break KSLR in order to provide this particular functionality. Generally speaking, when you're writing device drivers, you have access to these functions. Internal kernel code, you have access to these functions because you need to, because they're doing things at such a low level where you don't need to break KSLR. This is a highly specific scenario where I needed to break it in order to get the sort of functions I needed to protect memory. Otherwise, it would have just been read-write. Mostly read-write. I think all of it would have been read-write. None executable, which means I wouldn't have been able to actually execute this code in the kernel, which again is a security feature, right? Like you don't want people arbitrarily executing code in probably the most privileged piece of software on your computer, right? That's just recipe for disaster. Keys get stolen, lives get ruined, whole world burns on fire. I mean, it happens like last week with Amazon or something, you know. Like you kind of just roll with the punches on that one, really. So I don't know if that answered your question, but you know. Levi.
I'll just say it loud enough. So like, kind of in line with his question, when, like, do you remember the point when KSLR came into the picture.
I mean, it must have been in the 9s or something.
So did you see a performance like overhead from that?
No, there's no performance overhead. No, it's just an offset relocation.
Okay.
So there's no overhead. Now they are proposing, or there was a proposal within the last few years for what's called function level KSLR. So basically, you're relocating functions like individual functions. So yeah, there will be a load performance for that, a hit for that for sure. Yeah.
Along this same line of questioning, how long do you think until your app is obsolete? Is that tomorrow?
What do you mean my app? What are you talking about?
Your project.
Library.
Like the calculator?
Yeah,
When it'll be obsolete?
obsolete because of fixes.
For this workaround.
to
Oh
some of these workarounds.
no! You misunderstand.
Okay.
The point of this project was to read and write to a file. The security stuff was just a happenstance, like of what I needed to fix and work on to actually make this work in the kernel itself.
Oh, I
and
see.
if you actually implement your own runtime, right, you will have to contend with these security features yourself. So that's if I didn't make it clear, that was the whole point of this. It wasn't about like, oh, this is like a security thing bad, whatever, right, or anything like that. No. This is about I just want to load a freaking binary, and these are all the problems you run into doing so.
Why did you write a bmap to function in the kernel? Just to see if you could do it?
Yeah. I mean, I thought I was kind of a little clear with that. In case you missed it, I had an earlier slide where I wanted to actually use this in other languages without actually having to leverage libc or other sort of binding features of languages to use this functionality. So in order to do that, files were a natural candidate for that interface, for the fact that basically every language does deal with files on some level. What about Twitch chat? Anyone on Twitch chat? Man, we need to talk to chat. I gotta say chat at least once. Hey chat, what's going on? Any more questions?
So you're not going to DEF CON?
I'm not going to DEF CON. Why are you guys think I'm going to DEF CON? It's not a thing.
So what would be a normal way to load a binary?
I don't know how much detail I went into this in the slide before, but I had a slide with memmap syscalls. So what libc does is it takes whenever it loads binaries, it creates these memmaps. So this is memory mapped backed by a file is essentially the technical thing that's going on here. So what it does is at runtime it creates these memory backing of these files, and as you execute, it copies the data into those memory locations and then executes from there. So really, when you're executing programs, it's not really on the kernel level at all. It's mostly through the user space, as a matter of fact. The kernel is just usually responsible for allocating the memory needed to do so. Yeah. So everything's about the runtime. Oh, guys, Holy Trinity. All right. It's a thing. It's a thing.
Hello. I have a Linux question for you. I've been running Linux for about 30 years. What do you use on a daily basis yourself? And then does Cloudflare have their own Linux distro they use internally, or what do you guys use there?
Oh, I'm glad you asked.
Yeah.
I don't use Arch, by the way.
Oh, good. I hate Arch. No, I don't understand Arch.
Personally, this is Debian. This is Debian laptop.
Okay, that's what I use. That's what I got right here.
Oh, nice.
Yeah.
At home, I'm recently a Fedora convert.
Oh, okay.
Those who know me, I'm like, yeah, Fedora, right? Yeah, Fedora's great. But at Cloudflare, what do we use? We actually use Debian as
Okay.
well.
Okay. I thought you did. I just didn't know. But you guys probably have your own kind of packages and stuff you use
Oh yeah, absolutely.
internally. So.
Yeah. In fact, I actually gave a presentation last month. Last Dev Night almost in Austin, Texas, about some of the things we do with Debian packages to ensure integrity of them. So that's on YouTube somewhere for Linux Text Fest 2025. So you can watch that too if you're interested. Yeah.
So can I do an apt-get, Cloudflare, Cool Tools, and
I mean, I guess we have some public repository. I don't know.
I guess I could Google that and find out.
Yeah, thanks.
Thank you.
Are there any more questions? If not, I have a little spiel at the end. So.
One more shot.
All right.
At Cloudflare, either at a product level or finer grain, where do you generally, where's your space? What code are you writing and working on? Either at product level, or is it just across everything?
I do this.
You work on an old computer.
Who said that? Old
So-
computer? What?
So the system,
No, man, this is
level,
great.
not even really a product so much, down just below all the.
Yeah, I don't usually.
We're looking for a job description here.
Okay, I work on Linux kernel. That's what I do.
Okay.
And I maintain the operating system, the Debian operating system for Cloudflare as well. Yeah. Okay, we got more questions.
I got one more. So in the Debian vein, they've got one called Dev1. Have you messed with that? It's because they everything switched over. They all switched over to systemd a few years ago. Well, this is like a sysinit. It's for systemd haters, I guess. So I don't know if you've ever looked at that one, but it's Dev1, DEVUAN, I think. So it's currently they've been developing it for quite a while. They just had a new version come out. So I don't know what you think about systemd, but
I mean, I actually had a few incidents with systemd this last year.
Oh, okay.
Yeah, so I'm actually a fan. I mean, I have some open issues.
you're probably used to it and what it
Yeah,
does
yeah,
and how it does
I've
it,
read the
and why it doesn't do certain things.
Yeah, I've read the code. Yes.
Oh, okay.
Thank
you.
Yeah. Anyone else? No. Okay. One last thing before we wrap this up. Cloudflare is actually hiring 1,000 interns this year. So if you are a student or whatever, I'll have a link in Discord at some point this week. You might have to move to Austin, Texas, London, Portugal, take a pick, but it is a thing that's happening this year. So,
If anyone moves from Springfield because of that, I'm blaming you personally.
I mean, it sounds like you're interested. I don't know.
Sweet. All right, everyone give Fred a huge round of applause.